So let's now discuss numerical methods in solving differential equations. Numerical methods in solving differential equations. Okay, so here we'll see two methods basically. The Euler method, which is one of the basic method, and then the most popular method, the Runge-Kutta method. So basically the Runge-Kutta method. Okay, so Euler method is basically a single step method. And this is a this is also sort of multi-step method. We'll see more into that. Okay, so let's first discuss Euler method. We have seen basic types of so let's discuss the Euler method. So before discussing Euler method, what is the objective of the problem? The objective of the problem is, if you consider equation dy by dx is equal to f of x comma y, okay, and given that y of x naught is y naught, that is at x naught you know the solution of this differential equation, you know y naught. But now given any other abscissa, or given the abscissa x1 of any other point, I should be able to find out y at that point. That okay, we need to find ordinate y1, find ordinate y1. So that is the objective. Okay, if I know the x y naught at one position x naught, then given x1 I need to find, for any other x1 I need to find y1. So that's the objective. Okay, so we'll solve basically these two methods in order to see how these objectives met in these two methods. So Euler method. Okay, this was just the objective common in this numerical methods. So numerical methods apply to differential equations. Applying to differential equation more common because differential equations are tough to solve. Some even solutions doesn't exist if it's a non-linear higher order differential equation, solution even doesn't exist. So in that manner the only option is going to numerical methods. So let's see how do we apply Euler method. So what does Euler method says is that it says first, let me just, so we'll explain both along with the graph as well. Okay, so let's say you have a point x naught and you have a other point. Okay, and now at this point P, well, let me call this point as L. Okay, now I draw a tangent to the curve. Okay, and that say is h naught plus LH, and this is L1. So at this point, if I draw the tangent, and this is a straight line, so there's a straight line and there's a tangent. So tangent meets this h naught plus h line, vertical line, somewhere here. So let that point be P1. Similarly at P1, okay, so this is one thing. So what he says is divide the entire LM, this is L and this is M. Okay, so the first step is divide. So let's understand how this method is built and then we can lay down the final. So divide LM into n subintervals, each of width h, each of width h at L1, L2, so that h is quite small. Okay, and now in each interval, this is the crux of this method. In each interval, we'll approximate the curve by its tangent. We approximate the curve by the tangent. We approximate the curve by the tangent at the former point. By the tangent at the former point. So that's the thing. So at x naught plus h, the value of y will be basically the same straight line where it intersects this vertical line h0 plus h, and the straight line which originates being from a tangent at P. So that's the idea. Okay, so say in interval LL1 LL1 we approximate the curve by the tangent at P. That's what we have drawn, tangent at P. Okay, so the line through L1, so that is nothing but the line through L1 means vertical line passing through passing through h0 plus h, passing through h0 plus h vertical line. Okay, will meet this tangent at P1, will meet this tangent at P1. That is nothing but when P1 is h0 plus h1 plus y1. So this y1 is basically L1 P1, and this I can write LP plus R1 P1. So let's call this horizontal. So here you have something like this. You have P here, P1 is here, okay, and this is your R, and this was your L, this was your L dash, L1 basically. So L1 P1 I'm writing LP plus R1 P1. So this is R1. Okay, and LP is nothing but Y0. This is Y0. You know the solution at H0. And now PR is nothing but H. This this distance is H. R, so this I can write R1 P1 as, so this is theta. So R1 P1 I can write PR1 tan theta, right? PR1 is H, so H tan theta, and tan theta is nothing but the slope at, basically the angle made by the tangent. Okay, the tan of the angle made by the tangent at P, so that is nothing but the derivative H into dy by dx at P. Okay, so this is an important thing. So that's the idea. So y1 is approximated as y0 plus h into dy by dx at P, and dy by dx at P is nothing but the derivative of the function evaluated at point x0 y0. So that this is the basic equation. Okay, f dash in fact actually dy by dx is fxy. So from this you will, this is not f dash, this is f only. You will get h plus f of h0 y0, because the derivative are evaluated in P, and that comes out to be f. So the dy by dx is f of xy. Okay, now you have to proceed further in the similar manner. So now drawing the tangent at P1, which is h0 plus h y1, we'll draw the tangent, and let's its tangent at P1 meet the ordinate through L2. So that's what, meet the ordinate through L2 in P2 at point P2, which is h0 plus 2h minus y2. So basically you are approximating the curve by a straight line which is nothing but the tangent to the curve at the former point at the stars. So if you divide the interval into many small sub intervals, then this approximation will go worth, and you will get a reasonable approximation. So this is the way. So y2 will then become y1 plus h f of h0 plus h y1. Okay, so in the similar way you can proceed as many points you want. So yn will be yn minus 1 plus h into f of h0 plus n minus 1 into h into yn minus 1. So that's the idea. This is the general expression for the Euler method. Okay, so what we have done, we have basically divided it into equal intervals, and then at each interval we approximate it to be a tangent at the former point of the interval, and then we get a reasonable approximation to the curve at at x naught plus h. Similarly, you can proceed in the a similar manner. So right now, so this is the main crux of the story. Okay, so let's solve some problem in order to describe this method well. Okay, describe this method well. Okay, so given dy by dx as y minus x by y plus x with initial condition y of 0, that is at x equal to 0 y is 1. Now we need to find y for x equal to 0.1. So find y at x is equal to 0.1 by Euler method. So you know y at x equal to 0. You need to find out method in so divide, no, that's what he has given, divide 0 to 0.1 in 5 steps. Okay, okay, so that is actually left to us. I mean, you can divide 10 points if you want more and 12. So what we will do is we'll apply this basic equation, but let's draw a table here x y. So what I'll do is 0 to 0.1 I'll take 5 steps, I mean 5 steps, so such that n is 5 point sub intervals and h is basically 0.02, that is 1 by 0.1 by 5. Okay, so that's why 0.02. So now I'll draw a table x y, and then this is dy by dx is equal to y minus x by y plus x. Okay, and then now we have to basically write this equation. So this basically approximates new y is equal to old y plus h into dy by dx, and dy by dx you have to calculate at the old point or the former point, remember. Okay, that is the idea. So now x, you know, x is 0.0, so the points and axis, so it varies from 0.0, 0.02, 0.04, 0.06, 0.08 and 0.1. This is how x varies. Let's now compute all this. So y we know at 0 y is 1. Now the derivative dy by dx, you have to just substitute y and x here. Will be, you got 1 here, and if you substitute, now you have to approximate new y, which is nothing but 1 plus h is 0.02 into 1. So this gives rise to 1.02. So this is new y. Now okay, so now let's so now the new y becomes 1.02, and the derivative if we evaluate just substituting x and y, we'll get dy by dx. And similarly you have to now compute 1.02 is the new y plus 0.02 into 0.9615. So it's all, if you just lay down in terms of this, if you just write down tablet terms, you can just get the values clearly. And now the new value is 1.0392, and if you calculate derivative it becomes 0.926, and that is, you have to just substitute 926 and this value comes out to be 1.057. So you have to just repeat the process, and this is 1.0577, and this comes out to be, so this derivative comes out to be 0.893, and when you substitute all this in the differentiation, this comes out to be 0.893 is equal to 1.0756. So similarly 1.0756 here, and now if we calculate, this comes out to 0.862, and if you just evaluate this, so this once you write in a table it becomes very easy and avoids any confusion. So this becomes 1.0928. So the new value is 1.0928, and this is the approximation by the Euler method at 0.1. So the required approximation required approximate value of y is equal to 1.0928. Okay, so this is the required solution of this initial value problem using Euler method at point 1, given that x equal to 0 is y is equal to 1. So remember that if you want to solve this differential equation using analytical methods, you will be using this is a first order equation, differential equation, ordinary differential equation. So you will be basically, and this is homogeneous, each other term in the numerator and denominator is homogeneous, so you will be substituting y by x as v and then bring in terms of v. So this will be quite, I mean, it will require some labor, right? And finally you may have terms, log terms and tan inverse terms if you try to evaluate this. So instead of that, this method is quite simple, though it's approximate, but if you take more and more number of points, you can approximate a curve by a tangent, okay, in a very small interval. Okay, when n tends to infinity, this will be exact, this method will be exact. Okay, so that's the idea. So let's see other method, Range-Kutta method. The Range-Kutta method, which is another method and most popular method among the engineering community. The Range-Kutta method. Well, this has we'll deal with the fourth order Range-Kutta method, which is popularly called as Range-Kutta method. I mean, the fourth order term is not mentioned, but we will deal with only the fourth order method. Okay, so let's write down the working rule, because the derivation of this is quite tedious and probably not in the scope of this e-lecture. So we'll write down the working method and then we'll see how to apply this to a problem. So what it means is, uh, given that dy by dx is f of x comma y and y of x naught is, so y of x naught is y naught. Okay, that is what is given. So now what this method approximate is that y1 is y naught plus k. Okay, and k is called the increment in y, increment of y corresponding to an increment h in x, increment h of x. So now k is calculated as the weighted mean, okay, of k1, k2, k3 and k4. So k is basically 1 by 6 of k1 plus 2k2 plus 2k3 plus k4. So that's the thing. Okay, so once I know k1, k2, k3, k4, I can calculate k. Now the idea is, how do I calculate k1, k2, k3? So now we calculate successively k1, k2, k3, k1, k2. So k1 is h into f of x naught, y naught. Okay, so it's basically evaluating f at x naught, y naught and multiplying with h, that is k1. So once you get k1, k2 is calculated by this formula, x naught plus h by 2 plus y naught plus k1 by 2. So once you got k1, so now you have to evaluate the function at x naught plus h by 2 plus y naught plus k1 by 2. We will get k2. Now k3 is h into f x naught plus h by 2 plus y plus k2 by 2. Similarly, k4 is h f of x naught plus h y naught plus k3. That is your k4. So once you get k1, k2, k3, k4, you just substitute in this part, get k, and that is nothing but the increment of y. So this is a fairly simple working procedure. I mean, we'll not go into the detail in deriving it, but one thing is known, that Euler method. I mean, this method is basically the fourth order Runge-Kutta method, which is popularly known as simply the Runge-Kutta method. The Euler method was, you can term it as the Runge-Kutta first order method, but most of the time in commonly the common method that is used in solving differential equation numerically is basically this Runge-Kutta method, which is a fourth order Runge-Kutta method. Okay, so we have laid down the working procedure. The idea is just finally to compute k, which is again a weighted mean of k1, k2, k3, k4. So k1, k2, k3, k4 you have to just compute it independently and then find out k, and then that becomes the increment of y. So now let's apply those methods to let's solve some problems. Okay, so applying this Runge-Kutta method. Okay, so find out let's lay down apply Runge-Kutta fourth order. Write down these. I am writing out the statement to find an approximate value of y when x is 0.2, given that dy by dx is x plus y and y is equal to 1 when x is equal to 0. Okay, so now here same thing, it is given that x naught is 1, y naught is 1, y naught x naught is 0, y naught is 1, and dy by dx, you know, it is x plus y. So at x equal to 0.2 we need to evaluate y. Okay, so probably we'll do in one step only. So h is 0.2. Okay, and let's calculate now k1, k2, k3. So k1 is h, f, x naught, y naught. So just 0.2, and this is your f of x comma y. So substituting it, x naught is 0.2, y naught is 1. So this becomes point. Well, x naught initially it is 0, and this is x naught, so this is 0 initially, so this becomes 0.2. Now k2 will be h f of x naught plus h by 2 plus y naught plus k by 2, k1 by 2. Okay, so k naught plus h by 2. So now h is 0.2. Okay, x naught plus h by 2 is basically 0 plus 0.2 by 2, that is x value, and y value is y naught, which is 1, plus 0.2 is k1 by 2. So this comes out to be 0.2 into f of 0.1 comma 1.1, and this value is 0.24. Okay, so let's now calculate successively k3, k4, k3 is h into f of x naught plus h by 2 plus y naught plus k2 by 2. Okay, so that is 0.2 into f of, so if we substitute h by 2 and all that, so you will get 0.1 into y naught is 1, 1 plus 1.1 by 2, so that comes out, the value comes out to be 1.12, and if I substitute the values I'll get 2.440. so this is k3. Similarly k4, so the idea is you have to basically remember this h plus y naught plus k3, which is 0.2, and x naught is 0, h is 0.2, so this becomes 0.2 comma, and if you substitute y naught 0, k3 is 0.244, so this becomes 1.244, and this value comes out to be 0.2888. Okay, so now you got k1, k2, k3, k4, so this will be 1 by 6 of k1 plus 2k2 plus 2k3 plus k4, and this value comes out to be 1 by 6 of 0.2 plus 0.48, 2 times of 0.244 plus 0.24880 plus 0.2888. So this value comes out to be 1 by 6 into 1.48 0.2568 and so 0.2468. So this is the value. So the required approximated value is, the required value is y is equal to y naught plus k. Y naught is 1 plus 0.2468. So this value comes out to 1.2468. So this is the required approximation by the Runge-Kutta method. The required approximate value of y1 by fourth order Runge-Kutta method. Okay, so just it's quite simple. You have to just calculate successively k1, k2, k3, k4, then the weighted mean of that, which is k, and then you have to just add it to y naught. You may do it in, we have done in single step, you can do it in two steps. I mean, if you divide the entire interval into two, you'll get a better approximation. So now let's solve another problem on this Runge-Kutta method. So apply, the question goes like this: apply Runge-Kutta method to find approximate value of y for x is equal to 0.2 in steps of 0.1. Basically two steps you have to do. If dy by dx is equal to x plus y square, given y of 0 is 1, so basically at x equal to 0 y is 1. So here we need to solve this. Here we take in two steps, so h is 0.2 by 2, which is h is 0.1. Okay, and now we have to carry the calculations in two steps. Okay, so step 1, x naught is 0, y naught is 1, h is 0.1. So let's calculate k1. K1 is h f x naught comma y naught, which is 0.1 into f of 0.1. This is 0.1. Okay, similarly now k2 will be h of f of x naught, h by 2, y naught plus k1 by 2. So this comes out to be 0.1 into f of 0.05, 1.1. So you have to just substitute this h naught, y naught, h, k1 and substitute in f of x in the function. So you will get 0.1152. This is after evaluating. So similarly k3 will be h f of x naught plus h by 2, y naught plus k2 by 2. So this comes out to be 0.1 f of 0.5, 1.1152. So this comes out to be 0.1168. Similarly k4 will be h f of x naught plus h y naught plus k3 is 0.1 f of 0.1, 1.1168 comes out to be 1.1347. Okay, this was k4. So k will be basically the weighted mean. So this, if I just substitute the values, it comes out to 0.1 plus twice of this, so 0.2304, twice of this and twice of this, and then twice of this 0.1168 will be 0.2336 plus the k4 value. So this value comes out to be 0.1165, and therefore y of 0.1 is basically y naught plus k, which is 1 plus 0.1165, 1.1165. Okay, so this is at, we have approximated the value at 0.1. Now let's evaluate it in the second step, y of 0.2. In the step 2 we have to just evaluate x is what we know as x1 is basically x naught plus h, which is 0.1 because h is 0.1, x naught is 0, and y1 is 1.1165, which we just got, and h is my step. So based on this, now we have to evaluate k1, k2, k3, 4 again to get the value at 0.2. So k1 is hf x1 y1, because now this becomes a former point, and this is 0.1 f of 0.1 comma 1.1165, and this value if we calculate it comes out to be 0.1347. Okay, similarly K2 will be your HF H1 plus H by 2 plus Y1 plus K1 by 2, so that comes out to be 0.1 F of 0.15 to 1.1838, and this comes out to be 0.1551, and K3 is H F of H1 plus H by 2 plus Y1 plus K2 by 2. This comes out to be 0.1 F of 0.15, 1.94, 1.194 actually. Okay, by when you evaluate this, so this value comes out to 0.1576. So K4 is equal to H of F of X1 plus H Y2 plus K3, which is 0.1 F of 0.2 comma 1.1576. so this value comes out to be 0.1823. This is K4. So K is 1 by sets K1 plus 2K2 plus 2K3 plus K4. So this comes, if you just substitute all this, I get a value 1.1571. Okay, so Y is Y1 plus K, which is 1.1165 plus 0.1571. So this value comes out to be 1.2736 is the value at 0.2. So at 0.2 the value is 1.2736. So this is the approximated value. We have used two step in steps of 0.1 we have taken the interval of x, and that's why we have applied 2 times Runge-Kutta method. So this is how a simple you can just simply, so this is nothing, this is quite simple. You have to just apply that method step by step, calculate K1, K2, K3, K4, and then the weighted mean, and then just get the required value. So the basic idea is, so this is a multi-step method. Multi-step in the sense, it is formulated in such a way that in one step you can just calculate all this. Okay, so one of the advantage of this method is that the operation is identical whether the differential equation is linear or not. So that is one of the advantage. So advantage is that applicable for linear or non-linear. Okay, and the operation is identical. It is identical. The method is, it doesn't distinguish between linear or non-linear. You have to just apply this way. Okay, so what we have seen two methods, Euler method and the Runge-Kutta method. So Euler method, the basic idea was dividing the interval into n number of parts, and then each subinterval assuming the curve, approximating the curve to be a tangent at the former point. Whereas in Runge-Kutta method, it basically approximates the curve in the interval to be of higher order, and then uh, finally the working rule is written, and that we have written in the form of K1, K2, K3, K4 is calculated successfully, and then weighted mean is calculated K, and which is then added to it. So this is how a Runge-Kutta fourth order method works. So we have some other methods also, predictor corrector method, which is a multi step method, but the most popular method is the Runge-Kutta order 4 method, and the extensions are there. The Milne's method and the predictor corrector method. So those are all build up on this. First you predict a value and then correct it. So this is the idea about, so we have just introduced the most fundamental methods, the Euler method and the Runge-Kutta method for solving differential equations.